Hi, we are Group 12 from Session 23 and today we would like to present Chapter 7 from the Engineering Math 1, which is Cramer's rules about the many solutions. Let's start introduce myself. I'm Beijing, the leader of Group 12, and my members are Mirti and Wongkipo. What we can learn for after watching this video? We can use Cramer's rule for solving a system of linear equations. Secondly, we are able to determine the types of solutions, such as unique solutions, many solutions, and no solutions. For introductions, the Cramer's rule is a method used to solve a system of linear equations using determinants. The formula for solving a system of equations with n variables using Cramer's rule involves determinants and fractions.
If you have a system of equations Ax equals b, where A is the coefficient matrix, x is the vector of variables, and b is the constant vector, Cramer's rule for n equations with n variables steady state. If the determinant of the coefficient matrix A is non-zero, then the system of equations has a unique solution. If the determinant of the coefficient matrix A is 0, then there are either no solutions or infinitely many solutions. When determinant A equals 0, it indicates that the matrix is singular and the system can be dependent or inconsistent, resulting in either no solution or an infinite number of solutions depending on the specific equations. There are three types of solutions in Cramer's rule: unique solution, many solutions, and no solution. Firstly, we have to know row means number of non-zero rows within a matrix. For unique solution, row A equals row AB equals number of unknown in matrix equation. For many solutions, row A equals row AB but less than number of unknown. And lastly, for no solution, row A is less than row AB. Today, we would like to have a discussion of many solutions under Cramer's rule. So let's have a look for examples of many solutions. Given a system of linear equations in example 1 is 3x plus y equals negative 6, 6x plus 2y equals negative 12. Since we got two linear equations and two unknowns, which are x and y, then we obtain A as a 2 by 2 matrix. We fill in the first column with the numbers of x and fill in the second column with the numbers of y. Then we can calculate the determinant of A will equal 0. Thus, the solution is not unique. And we have to know that negative 6 and negative 12 could be a matrix B, which is a 2 by 1 matrix. And we write a new form of matrix by fill in the matrix A in front of matrix, and we have a line at the middle, then matrix B. And using the rank method, reduce the augmented matrix, we reduce row echelon form by elementary row operations, then we get the final matrix, which we will have a leading one in the column S, and the bottom rows will be 0. So from the new matrix, we can know that row A equals 1 equals row AB, but they are less than the number of unknowns, which is 2. Means that this system has many solutions. For solving this problem, just let y be the free variable, since column y doesn't have the leading one from the new matrix, and let y equals k. So we change the new matrix to the form of new linear equations. So x plus 1 over 3y equals negative 2, and x equals negative 2 minus 1 over 3y, and we change y to k. Then we can write our final answer by changing these new equations to matrix form. So we can know that k is within the set of real numbers.
Next, let us moving to example 2. The linear equation is shown as below. 3x plus 2y equal to 5, 6x plus 4y equal to 10. From example 2, we can obtain that the determinants of A is equal to 3 multiplied by 4 and minus 2 multiplied by 6 and equal to 0. So it means that the equation is not unique. By using the same method mentioned in example 1, we can get the final answer of the reduced row echelon form. And we can find that the row A is equal to row AB is equal to 1, and this is less than the number of unknowns, which is 2. Hence, the linear equations in many solutions. We can let y be the free variable because there is no leading one at the y column. So we let y equal to k and we rewrite the equations s plus 2 over 3y equals to 5 over 3, s plus 2 over 3k equal to 5 over 3, and the final answer is s equal to 5 over 3 minus 2 over 3k. And the k is all the real numbers.
Next, we come to example 3, which given a system of linear equations which are s minus 2y plus z equals to 1, 2s minus 5y plus 3z equals to 4, and 2s minus 3y plus z equals to 0. We can make the linear equation be matrix form, which shown below. By using rank method, reduce the augmented matrix to reduced row echelon form by elementary row operation and get a new matrix. Therefore, we can obtain that row A equals to 2 and equal to row AB, but it is less than the number of unknowns, which is 3. So, we can say that it has many solutions. By solving this example, we can let z be the free variable since column z doesn't have leading one, and we can let z equals to k. From the augmented matrix, we can get s minus 2y plus z equals to 1 and y minus z equals to negative 2. By back substitution, we can substitute z equals to k into equation. Then, we can write the answer in matrix form, so we can know that k can be any real number. For example 4, it is more and less like previous example, but for this example, it has a special thing, which is it has two columns doesn't have leading one, which are column z and column w. So, we let both z and w be the free variable. Hence, let z be k1, w be k2. By back substitution, substitute z equals to k1 and w equals to k2 into the equation. Then, we can find the solution, which is both k1 and k2 can be any real number.
For example 5, given a system of linear equations 2x plus y minus z plus w equal to 1, 4x minus 2y plus 2z minus 2w equal to 2, 6x minus 3y plus 3z minus 3w equal to 3, and the last one, at x minus 4y plus 4z minus 4w equal to 4. We can use the elementary row operations to find the row echelon form. After we get the final answer for row echelon form, we found that row A is equal to row AB is equal to 2. And this is less than the number of unknowns, which is 4. So the equation is many solutions. Let z and w be the free variable since the column z and w doesn't have any leading one. So let z equal to k1, w equal to k2. Since we have two row equations and the first one is s plus 1 over 2y minus 1 over 2z plus 1 over 2w equal to 1 over 2, and the second equation is y minus z plus w equal to 1. After that, we just substitute the value of z and w respectively to the equation 1 and 2. So we get the final answer x is equal to 1 over 2 and the y is equal to 1 plus k1 minus k2. Since the z is equal to k1 and w is equal to k2, so the value of k1 and k2 is all the real numbers.
For example 6, it is given that the system of linear equations which are x plus y plus z equals to 3, negative 4x minus 3y minus 5z equals to k, and 2x plus y plus 3z equals to 1. The question wants to find the value of k for which the system of linear equations has infinitely many solutions. By using RAM method, reduce the augmented matrix to reduce row echelon form by elementary row operation. Since we know row A equals to row AB, which is smaller than number of unknowns, we can confident that number of unknowns for this matrix is 3. If row A and row AB is smaller than 3, we can consider that row A and row AB is true. So, for third row must match all columns to be 0. Therefore, we can find the value of k which k plus 7 equals to 0, and we will get the final answer for k equals to negative 7.
In conclusions, we have learned that for the many solutions, row A is equal to row AB is less than the number of unknowns, and the determinant should be equal to 0. Last but not least, all the augmented matrix need to reduce to row echelon form by using the elementary row operation ERO. That's all for our presentation.